Okay. So I want to start off with a few corrections. I keep finding typos in my slides. There are two that are the more important ones. One is that, of course, I had, for some reason, 86 down as the number of elastic constants relating the stress and strain tensors. Those two tensors each have 9 elements, so of course the number of constants is 81, 9 times 9. I'm not sure why I had 86 there. The second one is that on slide 18, I noticed that a factor of mu was omitted from the second term in the right-hand side of the equation of motion in the x1 direction. So that equation should have read this, and this is the mu that was actually missing. I have forwarded Michael the corrected slides, and so I think that if you have recently downloaded the slides, you'll have the correct slides. Okay.
And Bill, if you would forward me these slides also, then I can also send out the corrections on sort of en masse.
I will do that. Okay. So let's restate the problem. The first problem that I left you with last Monday. So as we were talking about longitudinal wave reflecting from a free surface, so the boundary of a material where there is nothing but vacuum beyond that surface, I noted that the free surface velocity will be twice the in-material velocity imparted by the wave. And I asked you to show this to be the case based on the idea of impedance matching. Well, if we go back to the impedance matching, the continuity conditions require that the impedance matching, the impedance of the donor material times the initial velocity, which is the in-material velocity, the incident wave velocity, minus the change in velocity is equal to the impedance of the receptor or acceptor, the material into which the wave is traveling from the interface, the transmitted wave, times that same velocity, initial velocity, plus now the change in material velocity in the first one. And the reason for, as I noted, for the negative sign here is that the reflected wave is going in the opposite direction. And even though I'm not writing them as such, these are velocities, they're vectors, they are not just speeds. And so the vector quantities have to be the same. So in this case, effectively, when a wave is reflected into the material, if the wave, assuming it's a compression wave, if the wave is, if the wave that is reflected is also a compression wave, then that actually slows the material down in the laboratory reference frame. If it's a tension wave, then it actually speeds the material up. But fundamentally, this is the equation that we have to satisfy. Okay, well, the impedance, of course, is the sound speed or the wave speed times the density. So rho times CL for a longitudinal wave. The impedance of the vacuum is, well, zero, because it can't support a wave in the first place, and second, the density is zero. So in our free surface condition, this right-hand side of the equation is identically equal to zero, which means that the delta U1 has to take on a value that also causes the left-hand side to vanish. The only way you can really do that is if delta U1 is equal to the original material velocity, U sub I, so that the final velocity of the material at the surface and in the interior points as well, once the reflected wave passes those interior points, is actually 2 UI, or twice the end material velocity. So that's how we do that. It's almost a trivial problem, but sometimes people actually don't think about how easy it is to prove these things. Okay. Are there any questions concerning that before I go to the second one? So Michael, if you can, I can't see comments right now. If any show up, let me know.
I don't see any comments yet. So I suggest let's move on to the second problem, and then there may be questions towards the end, so then we'll field
okay.
those.
And also, if people want to, I can answer further questions about the material in general. Okay, the second problem.
And I would just add, because there's 16 of us right now, if you have a question, you can go ahead and unmute yourself and ask it. There's not so many of us that we have to necessarily use the chat box.
Okay, the second problem is only slightly more involved, but it involves something, a condition that could conceivably arise in some situation. So the second problem was using the Kolsky bar, which anyone who is familiar with material strength, dynamic strength studies has either used or at least seen data from the Kolsky bar, also known as the split Hopkinson bar. It's a widely used tool to study elastic and plastic properties of materials. And it consists of two long rods. The one that's more important for the purposes of our problem here is what's known as the incident rod. A longitudinal wave is sent down that long rod, and it's transmitted and partially reflected from a sample that's sandwiched between that rod and the other rod called the transmitted rod. So there's an incident rod and a transmitted rod. The rods are long and thin, so the wave that arrives carries uniaxial stress instead of uniaxial strain, as we were dealing with in the sound speed situation, where the two wave speeds, the longitudinal and shear wave speeds that we discussed during the lecture session. So let's assume the rods and the sample are isotropic, which is, at least for the rods, that is normally the case. They're polycrystalline steel normally, and the grains are reasonably randomly oriented. But let's assume the sample is isotropic too. And so there were two questions, really. One is, what's the speed of the incident wave as it comes through the incident rod? The second question was, what relationship between the elastic constants of the rod and the sample would result in there not being a reflection? So let's address that first one first. If you remember, for uniaxial stress, the relationship between the longitudinal strain and the longitudinal stress is sigma 1,1, the stress and the 1,1 component of stress is equal to Young's modulus times the 1,1 component of strain. I should point out some authors use a capital E for Young's modulus. The reason I don't is that in most shockwave work, which is really my specialty, E is the symbol used for internal energy. And so I took Y for the purposes of this discussion to be Young's modulus. Some people use Y for yield stress, and that's a different beast. But for our purposes, Y is Young's modulus. So now, if we think about Newton's second law, the force in this situation is due to the stress, obviously applied over an area. In the displacement, I'm back to calling displacement U, using U for displacement rather than velocity. So this is as I was using in the bulk of the discussion. So F equals MA, and skipping a few of the steps that we had in the derivation of the sound speeds or the wave speeds earlier in the lecture, we get this equation right here, rho times the second derivative of displacement with respect to time, so that's an acceleration, is equal to the spatial derivative of the stress. But since the stress is related to the strain, we can change these so that the rho times the acceleration is now y times the second derivative of displacement with respect to position. This is a wave equation. We're back to a wave equation, and the wave described by this equation will be propagating at a velocity equal to the square root of Young's modulus divided by the density. So as if you remember from the discussion on Monday, in a bulk wave, a wave where the strain is uniaxial, the longitudinal wave speed is the bulk modulus plus 4/3 times the shear modulus divided by the density. So it does have a different velocity in the long rod case than it does in the case of a normal, what we would think of as a sound wave going through a material. Okay, so now the second part, we're back to impedance matching again. Same equation, except for this time the receptor material, the sample, does not have zero impedance. So these have finite values on the right and left-hand side of this equation. Now, those of you who are familiar with the Kolsky bar will realize, okay, you know, I've set it up as the donor material as the incident rod, and the receptor or acceptor, some people call it, is the sample. There's another interface there between the sample and the transmitted rod, where the sample is now the donor and the transmitted rod is the receptor. Assuming the two rods are made of the same material, the situation that we have to meet for no reflection is going to be the same. And no reflection, in order to get no reflection, that means that the reflected wave, which is what gives rise to this change in velocity here, doesn't exist, which means that the change in velocity also doesn't exist. So this equation, the impedance matching equation, reduces to just Z1 times U sub I is equal to Z2 times U sub I. That means that the two materials, the rod material and the sample, have to have the same impedances. Doesn't mean they're the same material. Impedance is wave speed times density. So what it means is that wave speed times the density of the steel rod is going to equal wave speed times the density of the sample, whatever that sample might be. Expanding these out, what we get ultimately is that the square root of rho 1 times y1 is equal to the square root of rho 2 times y2, or more simply just rho 1 y1 equals rho 2 y2. And that's only possible if the Young's moduli of the two materials are related by the inverse of the ratio. The ratio of the Young's moduli is equal to the inverse of the ratio of the densities. So y2 over y1 equals rho 1 over rho 2. And of course, Young's modulus can be written in terms of the bulk modulus and Poisson's ratio and the shear modulus, or in terms of Lamé's constants. And you get, a somewhat messier relationship that involves all those things. But I'll leave it to you all to go do that. I'm too lazy. So that is the solution to the second problem. And are there any questions?
Thank you, Bill. Yes, time for questions. Go ahead.
Yes, I have one question about problem number 1. And in problem number 1, you show that the atom on the surface have the wave longitude and the wave velocity at 2 times at the atom next to them, but inside the material. And so it means that there's a discontinuity between the atom on the surface and the atom neighboring atom, but inside the material in terms of velocity.
No, there's not a discontinuity. The atoms at the surface are partially responsible for the potential well that the atoms deeper in sit. When those atoms move, they apply a force to the atoms that are next to them, causing them to move as well. And that is the fundamental origin of the wave that goes back, is that you start, if you remember in the discussion that we had of how a wave is generated, where I said, take, apply a time varying force at the surface. I didn't say what caused that force. Just apply a time varying force. It causes the atoms to displace, but then those apply a force because they have now the potential wells in which adjacent atoms sit have been distorted. And so those atoms are forced to move, and then they force the atoms adjacent to them to move, and so forth and so on. So you get this disturbance that propagates. This is the same thing. It's just that the force, if you will, that is applied at the surface was due to the arriving wave, and because the atoms at the surface, if you think about it, the potential well they are sitting in is only half as deep as the potential wells of the atoms in the interior. There's less resistance to them moving, and they move. But when they move, they then apply what is a net attractive force to the atoms that are deeper, because they displace the minimum in the potential well. And those atoms are then forced to move in the same direction. But again, with a time lag, so the distance between the atoms will be, if it's a compressional wave, the distance between the atoms will be increased. So it becomes a tension, a dilatation rather than a compression. And that will be the sense of stress and strain in the reflective wave. So there's not really a discontinuity. Yes, the surface is a discontinuity, but there is no discontinuity thinking in terms of a continuum. Remember, at the atomic level, no material is a continuum. And so some of our normal ideas break down. But if you want to understand the fundamental reason why materials do what they do, you have to think about it at the atomic level.
Thank you. Yeah.
Bill, do you mind if I ask a question?
Sure.
On problem number 2. So I thought that was I thought that was a very interesting problem, because when you are deforming a bar that has free surfaces on the sides, then during the deformation, those surfaces are going to move outward during compression.
They do. Yeah.
So that means that you're not going to have acceleration just along the bar axis. You're going to have acceleration lateral to the bar axis also.
That's correct.
However, only looking at the equation for the acceleration along the axis and not for the accelerations lateral to the axis. Why is that?
Because, well, the accelerations lateral to the axis are due to, kind of hard to discuss it conveniently. The accelerations lateral to the axis are due to, if you will, induced stresses. The initial stress that is applied to the bar is strictly sigma 1,1. But there are off-diagonal components in the elastic constant matrix that allow that to relate to the strain in the lateral direction. However, from the standpoint of the wave equation, we can write the wave equation for strictly one-dimensional, the linear or the longitudinal strain related to the longitudinal or stress. In the case of the bulk waves in uniaxial strain, there are other stresses there. Obviously there is a stress internal to the bar that causes acceleration, but that stress is strictly due to the sigma 1,1 is due to the relationship between the, well, it's due to the Poisson's ratio, and it's related to sigma 1,1. It's not a very satisfying answer, but from the standpoint of the wave equation, you have an acceleration, and you have a stress, you have a displacement, and those are the two things that make the wave equation. So even though there's lateral strain, and therefore there is, one can think of a volume strain, one could write down a somewhat more complicated expression involving volume strain, but the wave itself can be described strictly in terms of acceleration and the displacement along the same vector direction as the acceleration. So the stress being 1,1, we can treat that acceleration as strictly along the, if you will, the x direction. Ideally, you know, the equations really apply to an infinitely thin rod. So it's an approximation, but the real life Kolsky bar is generally, it's designed to where the length of the incident rod is such that due to reverberations, the lateral stresses are relieved by the time the wave gets to the sample.
Okay, thank you, Bill.
Mm-hmm. I had actually sat down and thought about trying to do it with involving all the strains and everything, and decided that it didn't really make sense to try and do that, because the basic equation that you end up with is the equation that you end up with.
Okay, thank you very much. So other questions? All right, if there are no other questions, then Bill, I'll thank you very much for giving us this rundown to the solutions. Hope that everybody has a great weekend, and Bill, we'll look forward to seeing you again on Monday, right?
Yes.
Excellent. Great. Well, have a great day, everybody.